Welcome everyone to the design reveal of the 9th team of Electric Superbike Twente. My name is Max and this is Sam, and together we are the management of this year. Welcome to the University of Twente, where it all started 9 years ago. Back then, a group of students founded Electric Superbike Twente with one vision in mind: to preserve racing for future generations. From back then until now, we have designed, built, tested and raced with 6 generations of superbikes. Right here with the bikes with us, we can see the evolution in real time. Over here we have Vector ST. Vector was a real powerhouse. It was developed for Moto-E level performance and innovated with the new battery swap system. This solved the problem of range, which was one of the biggest problems in electric racing.
However, we realized that innovation is not all about building the most powerful motorcycle possible. We realized that innovation is also about optimization and precision. That is why we switched to a different competition called Moto-Student. In this competition, we compete against 40 other student teams who built a motorcycle for the best performance possible within a given set of regulations. Here, you cannot simply win by adding more power. You win by out-engineering the competition. Last year, we were the first team to compete, the first Dutch team to compete in this competition. The goal was to prove that we could compete, and we succeeded. We won the Rookie of the Year award that you see right in front of us. To Electric Superbike Twente, this resembles the start of a promising new chapter. We stood out amongst the newcomers, but that won't cut it anymore for the upcoming years. The only thing left to do is to keep innovating and improving until we climb to the top step of the podium. So, a new year means a new team. We are 16 motivated and driven people ready to start working on the most important student project of their career. This is us, EST9. We have the Powertrain sub-team, which is responsible for the electric drivetrain. We have the chassis sub-team, who is responsible for everything structural. And we have the communication sub-team, who is responsible for making sure we look good to the outside and that everyone is up to date on our progress. So, we have 16 motivated and driven people, but we have an empty workshop for now. So what are our goals? What are we aiming for? What do we want to achieve this year? At the start of the year, we defined that in order to go to the top of Moto-Student, a simple evolution of our design wouldn't cut it. We needed to make an entire new redesign if we truly were to compete at the top. So, we defined 3 main improvement factors. The first one being a reduction in weight, the second one being more efficient systems, and the last one was more reliability. So, through a slimmed down design, through more integrated systems, and through a focus on reliability, we want to aim for the top of Moto-Student.
So, where does that leave us? How do we prepare for a competition even if it's still quite far away? Allow me to take you through the process of innovation and decision making. You might think it would look something like this, with the beginning and the end of your project and a few ideas or obstacles in the way. This year we found out it looks nothing like this. In actuality, it looks more like this. Step 1 is always starting with brainstorming, getting all the ideas out there, no matter how crazy or improbable they might sound. Next up, we start thinking, okay, how feasible are these goals? How well will this work? Where will we put our finances? Where will we put our manpower? What is the best solution for our bike? And once we made these considerations and calculations, the path to our goal becomes quite clear. This way, we make sure we leave no stone left unturned, and we build the best bike to our possibilities. And now that we've talked enough about the process, Sam, don't you think it's time to show them the fruit of our labor?
I think it's time. I think it's time to unveil our next generation electric motorcycle.
Wow, what a beauty she is. Nexus, meaning connection in Latin, is the name of our new bike. We couldn't think of a better name, since it resembles the core of a very complex structure. Now, we have many connections in our project. The first is through educational. Educational, we have ROC students, Saxion students, and University of Twente students all collaborating on the same project. Next to this, we run a very multidisciplinary team, where the electrical engineers, the mechanical engineers, the communications students, and the management students all work together and make friends along the way. Furthermore, the industry helps us out so much and is really the key to our success. All our partners, which give the opportunity for our young talent to work with and learn from the experts in the work field. And on that note, I want to give the word to our engineers who worked so hard on this design. So right now, I want to give Marnix and Jelle the word, and I want to ask you all to give them a well-deserved round of applause.
Hello everyone, my name is Jelle, and I'm this year's Chief Powertrain.
Hi, I'm Marnix, I'm Powertrain engineer, and I focus mainly on PCB design.
At the start of this year, we started with one thing: analysis of the previous Superbike, Mirage Evo, built by EST8. And from this analysis, we set out 3 goals for our design. First, more speed. Simple, we want to go faster. Second, reliability. We don't want any crucial connections to get loose at moments that are very unfortunate. And lastly, reliability and efficiency, by the way, which is very important, as if we handle power more efficiently, it brings benefits at all aspects. But how do you actually go about designing the electric powertrain of such a bike? Well, let's follow the flow of energy and start with the battery.
So like any battery pack in any electrical vehicle, our battery pack consists of many of these individual smaller battery cells. These cells have specific requirements, like the cells you put in your TV remote. Usually you don't put in just one of those AA batteries, but 2. We use the same principle. By combining more batteries, we actually build one very big battery. Our battery has some more requirements than your TV remote. We require very high peak power, so we can supply our power demand. We also need very high energy density, so that the cells that we use are very lightweight for the power that they produce. Other than that, we like battery cells with a very good geometry. I mean, they need to be assembled into a bigger system and have nice shapes, so good geometry is very nice. Other than that, the battery pack that we use in Nexus is inherently different than those you see in normal electric vehicles. I mean, we're not driving to the grocery store every day, we're not driving to work, we're driving a race of half an hour. We need peak and burst performance. That's why we have less requirements on our thermal stats of the battery, whereas normal electric vehicles need very stable thermal conditions throughout their lifetimes. We can actually dissipate all the power that we have in our battery in just one race of 30 minutes and do not really care about the longevity of our bike. That means that our cooling system is way less complex than those in normal electric vehicles, and we can save a ton of weight by just doing that.
Yeah, so enough about the theory. What do we actually choose? Well, the first choice to make is, do we choose rectangular, so-called pouch cells, or do we choose round, so-called cylindrical cells? Even though you can stack these rectangular cells together very efficiently, much like you can also stack bricks together very efficiently, they also have a downside, as because they're only encased by a plastic pouch, in case of a puncture, there's a high chance of aggressive combustion, which is something we definitely do not want. These cylindrical cells, however, when you stack them together, they leave more air gaps in between them, making them less efficient. However, because they do have a steel casing per piece, they are less prone to puncture. Additionally, because of their tabless construction, it is very nice to our heating strategy. That is why we eventually chose for these cylindrical cells.
Okay, so we now know a bunch of theory about these individual cells, but how do we go from here? How do we build something bigger?
Yeah, well, of course, yeah. We don't just have one cell, we actually have more than 500 of these in our bike. And then we connect them in two different ways. First, we take groups of 17 cells, and we connect them in parallel, meaning that we connect all the positives together and we connect all the negatives together. Then, we take 30 of these groups, and we connect them in series, meaning we connect the positives and negatives with each other. The cells in series act to increase the voltage of the battery up to 126 volts, and the cells in parallel act to increase the capacity of the bike, making sure we can drive some 50 kilometers on track.
Well, sadly for us, we cannot easily just connect these cells with wires or just by soldering together with one another. We need something bigger. We actually use these big metal plates. They're called bus bars. And usually they're made out of copper, because copper is a very good conductor. It's also very cheap. However, copper is quite heavy, and we hate everything that's heavy in our bike Nexus. That's why our mechanical engineers started calculating maybe we can use aluminium and get them to have the same electrical specs as copper, but with less weight. And in fact, it worked. So we're going to use aluminium bus bars, which are greater in volume, but that decreases their resistance back, just like a copper bus bar would have done. Within these aluminium bus bars, we inserted nickel, so that we can spot weld the cells onto the aluminium bus bars, and on top of those bus bars, we actually put thermal pads that are non-conductive, so that the heat that is trapped within the battery can escape to the casing and to the outside of the battery. Once this all is done, the battery actually consists of two identical modules that are manufactured the same way, and thus it's very easy to maintain them in the long haul. Those two modules have an air gap in between them. That's very efficient for passive cooling by air that just pass through them while driving.
Indeed, this pack is a real monster. Just to put its power into some perspective, let's just say we connect something to this battery pack. It can connect, or it can power 30 wall sockets to its maximum power, all at the same time. Or 10,000 phones, also, all at the same time, coming from power just from this battery pack. There is, however, also a downside to having so much power in a box. As a different shooter team recently found out, mishandling a battery is not something you want. That is why we carefully monitor everything that happens in our battery pack.
And we do so by adding the battery management system. The battery management system is a necessity in any electric vehicle you will probably have ever seen. Without it, it is unsafe to handle these machines for any human. Our battery management system is now custom made, and we're happy to tell that it's better than ever. The battery management system is best viewed as a company with a very strict hierarchy. In a company, there is a boss, and he can tell his employees to perform certain tasks and then report back to him what the results were of performing those tasks. Well, we can begin by explaining this company that we've built by beginning at the manager or the boss, the Battery Management Unit, or BMU for short. The BMU is the brain, and it's the beating heart behind the entire battery management system. It is the only component in the system that can perform analysis on actual data. Whenever a component outside of the system needs to know something about the BMS, it contacts the BMU. I mean, he knows what's up everywhere in the BMS. Other than that, the BMU has been custom designed this year, and the area has been reduced by 75% in comparison to our previous boards.
So then, up to these employees. The first employee of the BMU is the CMU, short for Cell Monitoring Unit. It is responsible for measuring all voltages and temperatures of the cells in the bike. We actually have two of them to make sure that all of these cells are covered. Most of the data that the BMU processes is actually obtained by these CMUs. This year, we're also redesigning them completely to make them custom, allowing us to have better charging performance and better balancing performance. Then we go to the Insulation Monitoring Device, or IMD for short. This is maybe one of the most important safety things in the battery pack, as this tells the BMU if there is a short to ground, meaning there is some high voltage coming to the chassis of the bike. And if that's the case, it tells the BMU, which makes sure there's no power flowing outwards, making the bike safe.
And then the last employer of our company, the Battery Disconnection Unit, or the BDU as we call it. It is actually just a block of relays, and those relays are, well, assisted by the BMU, you might say. Whenever the BMU, as the boss, runs into some kind of error or sees that the voltage or temperature is running too high, it opens up all the relays in the BDU, blocking all high voltage current from flowing anywhere, keeping all the energy within the battery pack. Now, we have actually rounded up our battery management system and our battery system as a whole. We have shown you how energy may be collected from different batteries and output under the safety critical features of the BMS.
So then, onwards, we follow the flow of the power. We go to the inverter, which is responsible for converting the DC power into three-phase AC power, which is power the electromotor can actually use. More on that later. This year, we're working together with the manufacturer to make the inverter even more efficient, directly correlating to speed on track. From the inverter, we go to the electromotor, which is actually supplied by the competition, Motor Student, and we're unfortunately not allowed to change anything inside it. Now, you may think, well, if all teams in the competition drive with the same motor, don't you all go the same speed? Well, simply said, no, we don't. This is actually where we can differentiate ourselves from the competition, because of how we control the electromotor. All that software is running inside the inverter. Think of it this way. If you're riding a bicycle, you start by pushing down on the left pedal with your foot. At some point, it doesn't make sense anymore to push down on the left pedal, and you have to start pushing down on the right pedal. The better the timing is, the faster you can go. That is actually exactly what is happening inside our electromotor. To keep the analogy going, this year, instead of manually testing all of the optimal forces we should push down on the left and right pedal for each possible pedal position as well as speed, we're mathematically calculating the optimal values, saving time and gaining performance.
Okay, so we've now given a quick overview of how energy flows from a single battery into a bigger pack, into the inverter, into the motor, and how it is all controlled by the BMS. But the BMS can only really shut the power on or off. It can't really control the flow of it. It cannot really say 50% power now. And this is where the smarter part of our bikes come in, the low voltage system. This is the system that has a bunch of communication, and the communication is between all these different nodes collecting data on, well, temperatures within our cooling systems, our suspension sensors, our brake sensors. And with this, we can get a really good overview of how our bike is actually performing in the real world. All this communication is based on the CAN principle. CAN is a form of bus communications, allowing us to have all the nodes connected to one another in series instead of parallel, which would be one mass of wires. So we just have one smooth wire running throughout our bike.
But this is not exactly new. We've already used this. So what is new? Well, this year we're completely redesigning the hardware and software of the data gathering nodes in our bike. Not next to allowing us to use the latest automotive safety systems as well as AutoSAR software, it also allows us to implement something called CAN FD. Think of sending a CAN message like sending a letter to a friend. You are only allowed to send one letter per day to this friend, and this letter cannot be more than one A4 page long. Now, if you would want to send a very long message, this would be very unfortunate, as you would have to wait multiple days sending that message. However, with CanFD, we're actually able to send messages that are 8 A4 papers long, meaning we can send a lot more data. This is very useful for our data acquisition and allows us to implement more sensors, like temperature sensors, but also suspension and wheel speed sensors.
And last but not least, we decided to add live telemetry into our bike. Well, live telemetry probably doesn't ring that well to many people, but it's just basically adding a 4G SIM card into your bike. So we can communicate with it while we are in the pit box and the bike is out driving on track. So we can keep track of all the temperatures and voltages in our bike while it is still on track driving around.
Yeah, but Marnix, this doesn't really look like a bike yet, does it?
Yeah, I mean, I have to say it needs some wheels.
Yeah, well, let's just ask our chassis team to explain. Please welcome Rolf and Wout.
So, now we have all the electrical components of our bike, but we're still missing the mechanical components and the structural components. My name is Rolf, and I'm this year's Chief Chassis of Electric Superbike Twente, and I'm here together with Wout.
Hello, my name is Wout and I'm a chassis engineer, and I focus mostly on the frame and the layout design of our new Superbike.
Together with Jedrek, Anna, Casper, Tuin and Victor, we took on the challenge of creating a completely new design for our motorbike. At the start of this year, we started with making some goals for this year. We want to make our bike lighter, we want to make it smaller, narrower, and we want to include some innovative designs in our project. First, I think it's time to go back to where Powertrain left off. So here, we see the battery pack together with the electromotor and the inverter. As Marnix already mentioned, we managed to save weight for the battery pack of more than 25 kilograms. This is not only done by choosing different cells, but it is also done by changing the internal layout of the battery pack and the casing. But we need to mount this battery pack somewhere. Wout, can you help us mount this battery pack?
Yes. So mounting for the battery pack and all other components, we have a frame. It's the backbone of our motorcycle. But this is also where the layout considerations were made. For example, we can begin with the battery pack itself. It's placed right in the middle of the motorcycle, ensuring good airflow reaches the side of the battery pack, which cools down the cells. It's also really important for the location of the center of gravity, since the location of the center of gravity in a motorcycle is really a big player in determining the handling of the bike. For example, if you have a bike that has a really high center of gravity, it falls into a corner really quickly and really aggressively, but it can become too aggressive and unstable. But if you have a really low center of gravity, the bike is really stable, but it doesn't want to turn into a corner, so you keep going straight. So it's kind of a trade-off. So the battery pack is placed quite high. To balance it out, we've placed the inverter in the bottom of a motorcycle. And this has another advantage, because the inverter creates quite a bit of EMI. It's called electromagnetic interference, and it disrupts other electronics. So therefore we place it in the bottom, quite far away from delicate electronics, to prevent it from disrupting them. The placement of the electromotor is quite a bit more challenging, because there's a lot of force at play. The force of the chain pulling the rear wheel actually influences the rear suspension. So we've optimized the electromotor placement to ensure good power delivery and weight transfer while coming out of a corner. And then of course, we have the frame itself. The frame itself will be made out of 70-20 aluminum compared to old years which have used chromoly steel frame. This saves about 25% of the weight of the frame. We've chosen this specific alloy because it regains a lot of strength after welding, which is really nice for our use case. Another really big challenge for the frame design is getting the stiffness right, because the frame of the motorcycle has to absorb a little bit of bumps mid-corner to achieve a greater rider feel and greater grip mid-corner. So to balance out the exact flexibility of a frame, we've carefully considered the triangulation of the frame and therefore optimized it. But Rolf, I don't think we can mount our wheels yet, right?
No, indeed. We still miss a critical component, and that's the swing arm. Here you can see the new design of our swing arm. The swing arm is basically the component that connects our rear wheel to the frame. It's fully made out of aluminum and has a triangular structure. This triangular structure makes sure that our swing arm has a very high stiffness. However, during the design process of our swing arm, there were some challenges. One of these challenges had to do with the placement of our electromotor. For our transmission system, we decided to place our electromotor at this specific location. But that made sure that we were not able to make use of a pivot axle. The pivot axle is basically the place where the swing arm can rotate around. So we had to find something different. We came up with two pivot point connections. It can be seen over here, one on each side. These pivot point connections make sure that our swing arm is connected to our frame. But this came with another challenge, namely with the width of our swing arm. The width was too wide basically at the end of our swing arm. So we had to taper our swing arm inwards from the pivot point location to the end of our swing arm. But there's one more thing that I want to say about the swing arm, and that's the top mount suspension. The top mount suspension basically makes sure that our rear shock will be connected between our frame and our swing arm. Wout, can you tell us a bit more about the suspension that we have?
Yes, of course. So for both the front and the rear suspension, we use fully adjustable Öhlins. These are the top of the line in terms of suspension components, and they're actually quite similar to what's actively used in MotoGP. The nice thing about them is that they're really adjustable. We can adjust things like rebound, damping, spring rate, preload, everything. So as you can imagine, we can quite nicely fine-tune how the bike behaves in corners, accelerating, braking, everything. We can precisely control it. But to aid in us setting up the bike, we've actually implemented both front and rear suspension sensors. Those sensors gather data to what the bike is actually doing inside the corners or braking, everything. So we can use that data to optimize our setup for any use case, for any track, whatever we might come across. So that's really nice.
But Wout, we're still missing the wheels, right?
Yes, but now we can finally add the wheels. So in terms of wheels, we actually use wheels that are really similar to Moto-E wheels and rims. Those are supplied by the competition to keep things fair among other teams. But one nice thing about our wheels, for our case, is that because we made the battery pack and all other components of our bike more compact than before, we can actually reduce the wheelbase, so the distance between the front and the rear wheels. Reducing the wheelbase actually helps increase the handling and making it turn into a corner quicker. So that's really nice. Oh yeah, and for the transmission, we had a choice in the beginning of our year. We could choose between a direct drive system or a transmission. Almost all previous Superbike teams use a transmission because it allows for more freedom while placing the electromotor and other components. For our year, we decided to not do it. We decided to go with a direct drive system. This means we mount the front sprocket directly to the electromotor, and then with a chain, we power the rear wheel. This system is lighter, simpler, and it's also even more efficient than using a transmission. So more of our power, of our electromotor's power, reaches the rear wheel. Oh, with Rolf, I think we also need to cool the electromotor, right?
Exactly. Cooling is quite critical for our motorbike. There are two main components in our bike that need cooling. Those are the electromotor and the inverter. I will start with the electromotor. The electromotor actually gets quite hot during racing. There are copper windings inside, and a lot of current is going through these copper windings during racing. So it's critical that we cool the electromotor. However, it's also very hard to cool the electromotor. Both the electromotor and the inverter have their own cooling loop, and I will start with the cooling loop of the electromotor. Here you see the cooling loop of the electromotor. It contains a cooling tank, and inside that cooling tank there's water together with ice. There is also a copper thin tube inside the cooling tank, and water is running through the copper thin tube, and a lot of heat transfer can take place between the water inside the tube and the water and ice inside the tank. This is quite a new design, and it's quite innovative. Besides this, we have the cooling loop for our inverter. The cooling loop of our inverter contains a conventional radiator. Wind is hitting the radiator and it cools down the water inside the loop. The size of the radiator was determined by data from last year, from the race in Spain. We managed to decrease the size of the radiator by approximately 60%. So now we have all the components inside the bike, but we still need a place for the driver to sit on. Wout, can you help us?
Yes, of course. So in our case, the rider can sit on the subframe. For the subframe, we also had a choice to make. We could go for a conventional solution and put steel or aluminum tubes underneath the seat to support the weight of the rider. Or we could make it structural in itself. We have decided to go with the second option and make the subframe structural. This does mean that it has to support quite a lot of weight. Therefore, we've decided to make it out of a carbon fiber sandwich. A carbon fiber sandwich is 2 plates of carbon fiber stacked, and it's separated in between with a layer of foam. This actually increases the bending strength of the carbon fiber quite a bit compared to a flat sheet of carbon fiber. Next to that, there is another challenge with designing parts made out of carbon fiber. And that is that it's only really strong in one direction, and in the other direction, it's not as strong. So to optimize the placement for our carbon fibers and place the fibers in the direction of the load, we did a lot of simulations to actually determine what the optimal layup would be for those components. This means we can produce a really light but also really strong subframe. And with this being said, I think we can add our bodywork and finalize our bike.
Now we have all the components in our bike, and it's time to look back at the goals that we set up at the start of our year. We wanted our bike to be lighter, we wanted it to be smaller and narrower, and we wanted to include some innovative designs in our project. First of all, the battery pack alone is already 25 kilograms lighter than last year. Our frame is smaller and narrower than ever before, and we managed to include some innovative projects, like a cooling tank and a carbon fiber subframe. Now, with all the technical details being said, I think it's time to give the word back to Sam and Max. Give them a warm applause.
So far, we've taken a look at all the different individual improved components. But a single component won't win you the race. The entire integrated system does. So, as our technical team just explained, every single one of these design choices have been towards either one of the three goals that we set. From the aluminum frame to the integrated electrical systems, there was an aim to either reduce weight, to make the system more efficient, or to improve our reliability. But what does this actually mean for the entire design? Let's take a look at what it means for the performance of our motorcycle. In total, we managed to reduce the entire weight of the bike compared to last year from 185 kilograms to 145 kilograms, which is a decrease of around 20%. This reduction in weight and also the more efficient systems have reached a top speed of above 200 kilometers per hour instead of the 180 from last year. And finally, we managed to increase our 0 to 100 time from 7 seconds to less than 5 seconds. But this is only the start of our road to Motor Student in 2027.
Well, that's quite the difference. So, what's next? Right now, we're busy. We show you a bit about the status of Nexus TR as we finish the design, and we'll focus for the remainder of this half year on building it. So, you all can see Nexus TR in its full glory in July. Then we can give this project on to our successors, EST10, so they can test it vigorously. So we make sure that Nexus will hit the ground running in 2027 on Motor Student in the best shape possible. Next to Nexus, we also have Mirage Evo from last year. Together with our predecessors, EST8, we are working right now at the revival of Mirage Evo to make it shine once more. We are planning multiple events. Once where we drive through the inner city, the city center of one of the big Dutch cities with other student teams, and we have 2 race days at the end of the year planned. So stay tuned for these updates. Now that we've taken you with us through the past, the present, and the future, I want to invite our whole team on stage.
Give the team applause.
This is the end of the presentation, but not of tonight. On behalf of our whole team, we want to thank you. We want to thank you for your participation here tonight, for your interest in our project, and in your help. The presentation is done, but after this, we want to invite you to join us on the info market behind the doors behind you, where our engineers are eager to talk with you about the parts they designed. So have a drink at the bar, and thank you once more.